Hello friends, today we are discussing about electrostatics of metallic conductors. You know that in a metallic conductors there are many free electrons and all these free electrons are in random thermal motions. There is no preferred direction for these electrons. The average velocity of this electron is 0, or otherwise we can say there is no net movement of the electrons in the conductor. So we can assume it is in electrostatic conditions. At static condition there is no net movement of charges in the conductor. Now we are discussing some of the electrostatic properties of this conductor. Suppose we are placing such a conductor. Suppose this is a conductor, metallic conductor. In this metallic conductor there are many free electrons, and at this condition, in a static condition, total charge inside this conductor is 0. Total charge inside the conductor is 0 because equal number of positive and negative charges. So the flux through the conductor and the electric field inside the conductor is 0. Now suppose we are applying an external electric field here. Suppose if you are applying an external electric field, this conductor is placed in an external electric field. There is an external electric field in this space. The external is E outside. That is, E outside is the external electric field. Under this external electric field, all the electrons or all the charges experience an electrostatic force. It means that electrons are moving opposite direction of this electric field. So what happened? All the electrons are moving opposite direction of this electric field, and they accumulate on the left side here, in this side. Or otherwise we can say there is an accumulation of positive charge on the other side. On this side we have negative charges, on the other side we have positive charges due to the migration of the charges. And so these accumulated charges produce an internal electric field. Here we have an internal electric field, E internal. Internal electric field is produced inside the conductor. And at a static condition, the E outside should be equal to E inside. The internal electric field produced inside the conductor will be equal to the external electric field. So what happened? They are in opposite direction, so they can cancel each other. So net electric field inside this conductor again comes to 0. So we can say one of the electrostatic property of a conductor, metallic conductor, is inside the metallic conductor electric field is always 0. If it in static condition or if an external electric field is applied, we can say inside a conductor electrostatic field is always 0. Inside a conductor electrostatic field is always 0. That's the first property of a metallic conductor, electrostatic property. Then second property, at the surface of a charged conductor, electric field must be normal to the surface. Consider such a situation. Suppose we have a charged conductor, whatever may be the shape, we have a charged conductor. It's charged positively or negatively charged. Suppose this is positively charged conductor. This is a positively charged metallic conductor. So electric field lines are originating from this conductor in all direction. So these are the some of the electric field lines which are originating from this conductor. And you see that all the electric field, these are the some of the electric field lines. All these electric field lines are normal to the point to the surface. All the electric field lines are normal to the surface. Suppose if there is any electric field which is not normal like this, suppose if we have an electric field like this way, for this electric field line we have some other components. If you are finding what are the rectangular component of this electric field here, we have two rectangular component. Now this component is along the surface. So what happened? Under this electric field component, the charges on the surface will move. As charges through the surface move, it produces a current. Can be called as a surface current. But at static condition, no such current is possible. In static condition, there is no such surface current. So we can say all the these lines are not possible. All the electric field lines must be normal to the surface of a charged conductor. Second important property of a conductor, at the surface of a charged conductor, electric field must be normal to the surface. We have no electric field lines which are parallel to the electric surface or charged surface. Okay. The third property is that the net charge in the interior of a conductor is zero. That you already seen. The net charge inside a conductor is always zero because there are equal number of electrons and protons, or equal number of positive and negative charges. Suppose it is charged conductor. Instead of this uncharged conductor, suppose if you are taking a charged conductor, a conductor is charged. Suppose this conductor is charged externally, it is charged by some process, induction or some process. This conductor is charged. But you see that whatever the excess charge given to this conductor, it resides only on the surface of the conductor. We are giving some excess charge, but this charge resides only on the surface of the conductor. Because we already know that the electric field inside this conductor is equal to what? Zero. The electric field inside this conductor is equal to zero. And suppose in this situation, we are considering a Gaussian surface which is very close to the boundary of this conductor. Which is very close to the boundary of the conductor. So, by Gauss's theorem, if you are calculating the flux through this Gaussian surface is equal to Q by epsilon 0. The flux through this Gaussian surface is equal to Q by epsilon 0. But you know that electric field inside this conductor is equal to what? 0. As electric field is equal to 0, the flux is equal to 0. Why? Because you know flux is equal to surface integral E dot ds. E dot ds. So E is equal to 0. Since E is equal to 0, flux is equal to 0. So you can say Q is equal to 0. Q is equal to 0. Means what is the charge inside this Gaussian surface is 0. Already it is charged. Is it? It is charged conductor, but whatever the charge given to this conductor resides only on its surface. All the charges given for the conductor resides only on the surface of the conductor. That is the third point. The net charge in the interior of a conductor is 0 and any excess charge resides at its surface. Whatever the charge is given, it resides only on the surface of the conductor. And the fourth property, potential is constant within and on the surface of a conductor. That concept we already derived. We have seen that for a spherical conductor like this, suppose if we have a spherical conductor, a charged shell, suppose this is a charged shell. For this charged shell, this is a charged shell of radius r. For this charged shell, we already derive an equation. What is electric field due to this charged shell? And we seen that electric field due to a charged shell at inside is equal to 0. The electric field is equal to 0. But outside we have electric field. But electric field comes to 0 as potential is constant, because we know that electric field is equal to negative of potential gradient dV by dr. Electric field is equal to minus dV by dr. And E equal to 0 means V is a constant. V is a constant. It is not only for a spherical shell, it is applicable for all charged conductors. For any conductor, the V is constant throughout its volume, and it is same on its surface also. Potential is constant at everywhere inside this conductor. Everywhere, at all point, potential is constant, and on the surface the same value. But outside it is varies. And electric field inside of any conductor is always 0. That is the fourth point. The potential is constant within and on the surface of a conductor. Potential is constant, whereas electric field is 0 inside it. Okay. And the fifth point, the electric field at the surface of a charged conductor is proportional to the surface charge density. Electric field at the surface of a charged conductor is proportional to the surface charge density. Let us how to prove that. Suppose if we have a conductor here, this is a regular shaped conductor having a surface charge density sigma. It having a surface charge density sigma. And now suppose if you are imaging a very small cylindrical Gaussian surface here, a very small cylindrical Gaussian surface, and it's one flat, half of the cylinder is inside the metallic conductor and half outside. And suppose this flat surface area is delta S, a very small area delta S. If you are calculating what is flux through this Gaussian surface, you know that electric field lines are normal to the surface, so flux contributed by this curved surface is 0. The flux is contributed only by this flat surface having an area delta S. So what is flux? Flux is equal to E into delta S. E into delta S. And by Gauss's theorem, it is equal to what? Q by epsilon 0. Q by epsilon 0. Actually, I told flux is only contributed by this surface. That's why E into delta S only. E into delta S. Only delta S area contribute flux. And what is the charge inside this Gaussian surface is, the charge inside this surface is Q. Q is equal to what? Sigma into delta S. So we can write E into delta S is equal to sigma into delta S by epsilon 0. E into delta S is equal to sigma into delta S by 0. Delta S and delta S can be cancelled, and E is equal to what? Sigma by epsilon 0. For any charged surface, whatever may be the shape, the electric field is proportional to surface charge density. That is this point. The electric field at the surface of any charged conductor is proportional to the surface charge density. That is what? E is proportional to sigma, surface charge density. Electric field due to any charged conductor is directly proportional to its surface charge density. E is directly proportional to sigma. And another important property of a metallic conductor is that we already see inside a metallic conductor, suppose we have a charged shell, this shell is charged. Inside this shell, the electric field is always 0. Inside this shell, the electric field is 0. And suppose we have a large cavity inside this shell. This is a metallic shell. Okay, inside this metallic shell we have a cavity. And see that inside this cavity also electric field must be 0. Inside the cavity of any metallic block, the electric field must be 0. So this is very important property in electrostatics. we calling this is electrostatic shielding. Actually, this region is shielded or protected from external electric field. If you are placing such a metallic block inside a electric field, suppose we have a strong electric field and we are placing a metallic block inside this electric field, and suppose we have a cavity inside this metallic block and electric field is always zero. Whatever the strong electric field we applied, the electric field is always zero inside this cavity, or otherwise this region is protected from electric field. This cavity is free from electric field, or that region is protected from external electric field. This phenomenon of protecting any region from electric field, or that process we can call as electrostatic shielding. Some sensitive devices or electronic components can be protected from external electric field if it is placed inside a metallic cage. So that process is known as electrostatic shielding. Inside a metallic shell, electric field is zero. That region is free from external electric field. So any electronic devices, if you want to protect from external electric field, you can keep inside a metallic block or metallic cage. That is known as electrostatic shielding. Thank you.